All right, this is a question from the Chapter 4 review in Stewart. It's an extreme value question. You can see in part A, it says, at what numbers does G have an extreme value? It says an extreme value, not the extreme value. And they don't give you any kind of an interval to restrict it. So we're talking about over the entire domain. So the context tells me there, at what numbers does G have an extreme value? The way that's being asked, first of all, an extreme value would be a relative maximum or minimum, or a local maximum or minimum, not necessarily an absolute max or min, right? Although, since we're talking about the full domain of the function, it could also be, one or more of them could also be that. And then the fact that it says at what numbers does G have this? We're talking about X values then, like at what X values, right? It's not saying what is the value of G, like what is the extreme value of G. It's saying where does G have the extreme value. So this part means like we're talking about the location, like on the x-axis, right? So X value. And this part means relative or local extrema. So those are, first of all, we got to be able to interpret that. Okay, and then B, discuss the concavity of G. So we'll be looking at like a sign chart there on F double prime, which, we can get from the information about F's concavity. Oh, I guess, you know what? It's interesting. They're telling us the concavity of F. Oh, of F. Yeah. We got to look at G. So we'll have to do a sign chart on G double prime. Okay. Yeah, so that's the other piece of this, the way they define G. And this is very typical on the AP exam, by the way, too. They love to, without telling you like an algebraic function or even a graph of it or tabular values or anything like that, they just give you some other information, some information about F and define G in terms of F. Or sometimes they'll do, they'll give you K of X equals like F of X over G of X, right? And then you're looking at like a quotient rule or something like that. These are very typical AP questions. You have to think about what kind of a function is this? This is a composition, right? This is F of X squared. So on the inside, you have the X squared function. On the outside, you have F, whatever that is. And so when we're doing a derivative, we're going to have to use the chain rule. And that's part of what they're testing here. So that's the first thing I'm going to do. If I want to talk about relative maxes and mins on G, I need G prime. And if I want to talk about the concavity of G, I need G double prime. So let's start with G prime. And I'll just go ahead and label this as part of A's work, but we're going to use that G prime in B also in order to get G double prime. So G prime of X equals, and what do we know? Well, this is G in terms of F, so let's start with that. It's a chain rule situation. You have a function inside a function, so you take the derivative of the outer function, F, keep the inside the same, and then we multiply by derivative of the inside, right? Whoops, 2x. By the way, I recommend when you're doing any problems like this and watching a video to help, as soon as you get an idea, something where you had been at a roadblock, pause. Pause the video, work it out yourself. When you get stuck again, hit play. If you want to double check something, hit play and pause again. It'll work for you. The more you'll learn is what I've learned in my learning and teaching career. Anyway, that is G prime, right? F prime of stuff times stuff prime. All right. So we want to know where G has an extreme value. That means we need to know where G prime, either equals 0 or does not exist, right? That's how you get critical values of G. So I'm just going to go ahead and write down G prime equals 0. And that's going to happen when F prime of X squared equals 0 or when 2X equals 0, both of those. Let's start with a 2X. That's a little easier. 2X equals 0. So, hey, that means X equals 0, right? That double arrow means implies. That's a mathematical symbol. So I had an equation here, and then it implies this equation or this solution follows from it, basically is what I'm saying. All right, and then the other possibility is F prime of X squared equals 0. What do we know about F? Well, we know F prime of X is greater than 0 for all X not equal to 0. And we also know that F is twice differentiable for all X. So f prime of 0, that means f is also once differentiable, right, for all x. That means f prime of 0 does have to exist. And so it doesn't tell us exactly what f prime is doing at x equals 0, right? We just know that f prime is positive for all other values. You might think that implies that f prime of 0 is 0. Well, not totally though, but we do actually know that g prime of 0 is 0 already because we just did that. So it kind of doesn't really matter, I guess, is the point. Um, the only place that we could get this is where x squared equals 0. I'm just going to kind of write that down. X squared equals 0 with a question mark, and x equals 0 follows from that. So we already knew that, right? We already know that x equals 0 is a 0 of g prime. And so there's nothing else. There's nothing else we're going to get. Every other value of x here will yield a different input to f prime. And we know that that means f prime is going to be positive for all of those values of x. Okay, so in fact, we could write that down. For all x not equal to 0, f prime of x squared is going to be positive. We know, right? And so this is unimportant. We already had x equals 0. All right, that's really it. You can also consider places where g prime does not exist, right? You want to think about that. G prime of x does not exist. And, I already know the answer to this. They tell us f is twice differentiable for all x. G is f of x squared. X squared is infinitely differentiable, right? It's a polynomial or power function where, it's not going to, polynomial function. It's a power function with a positive integer power. So it's definitely infinitely differentiable, right? That second derivative will be 2, and then after that, the derivatives are all 0, but they do exist. So the point is, um, if you take a function f that is differentiable everywhere of another function that is also differentiable everywhere, you do get a function that is differentiable everywhere. And so g is twice differentiable everywhere. So this has no solution is my point, because for g prime to not exist, that would mean g is not differentiable somewhere. I'm going to write it down. I'm going to be very thorough here. G is twice differentiable because everywhere, right? For all x, for all real numbers x, what that means, because f is twice differentiable, and so is x squared. Okay. So again, being very thorough here. If your goal is just to get to the answer, we could have probably done it by now. But justification is it's an important part of math and calculus and AP calculus. All right. So the only place we have to consider our only critical number is this one, right? X 0 is the only critical number of G. And so when we make our sign chart for G, that's going to be our main value there, our only value. So you can do 0 and then sign chart for G prime is what we want to do. And, F prime, we already said F prime is positive for everything except 0, right? And since G prime is F prime of these values that aren't 0, because 0 is the key number there, G prime's the F prime of those values and then times 2x, right? So those are the factors. Here, let's write those down underneath if you want to kind of think of it as a more detailed sign chart. So f prime of x squared, my point is f prime is going to be positive on both intervals, and then the 2x factor in g prime, that is going to change signs from negative to positive at 0, and that's it. So g prime is negative here because a positive times a negative, and it's positive here, positive times positive. So what does that mean? That means g has a relative what at x equals 0? A minimum, right? Because G prime goes from negative to positive there. And this looks like a winking person who's surprised or something. I don't know. Anyway, the face there. Anyway, so G has a relative min. This is the answer to the question of part A, by the way. G has a relative minimum at x equals 0 because G prime changes from negative to positive there. All right, and what I always say in class is giving any kind of statements where you need to justify function, behavior, location for every part of it. Function, behavior, location, very clear answers to that for what our conclusion is. And then same thing on the justification, function, behavior, location. And there is a pronoun, but it is a very clear antecedent. And so as long as that's all covered, we're good to go. All right, FBL, function, behavior, location. That was part A, all done. All right, part B, and we'll go a little quicker this time, discuss the concavity of G. So for that, we need a second derivative, right? G double prime of X. And so we're going to start from G prime of X. This is part B. And G prime of X was F prime of X squared times 2X. Maybe I should write that again really quick so we can see it. Here, I'll just write it here. G prime equals F prime of X squared times 2X. We're going to do a product rule now with the chain rule, right? So I've got like my U and my V. So my U prime, I already know U prime pretty much, right? It's going to be F double prime of X squared times 2X, right? So F double prime of X squared, and then times a 2x for the chain rule. But then that's U prime. I still have to multiply by the V, which is another 2x. So that gets squared plus, and then F prime of X squared times 2. So I'm just going to put the 2 out front. F prime of X squared. All right. And yeah, that's it. It looks messy, right? This is tricky because we have the second derivative of F and we have this first derivative of F, both of X squared. And then we also have the 2X quantity squared there. I'm going to go ahead and we could probably analyze it right from here. If you wanted to, you could also factor out a 2. To do that, you'd want to make this like a 4x squared. I don't know, maybe I should just write it that way. 4x squared F double prime of X squared plus 2 F prime of X squared. And that is it. There's nothing else in this factor, right? There's no like X factor on there. So just keep that in mind. And you can't factor out, like if you're tempted to try to factor out the X squared, you can't do that. It's inside of two different functions here, F prime and F double prime. So this is it. We just have to look at each of these separately. So what do we know about F prime? Well, we talked about this already. F prime, we were told that F prime is greater than 0 for all X not equal to 0, right? So that's still true. So this part's always positive except at 0. So 0 might still be a thing. Let's go ahead and start a sign chart just to kind of think about this. And maybe we need some other stuff here, but we'll talk. But the F prime of X squared times 2, right? That's not going to change its sign. And to the right of 0, right? So positive values of X, that's definitely going to be positive over there. And then to the left of 0, same thing. As long as X isn't 0, yep, that factor, and it's not a factor, that term is going to be positive everywhere. Be careful though here. This isn't like an ordinary sign chart because this is a term, not a factor. It's not multiplied on the whole thing. So you can't like, if I put this other term, so this is, here I'll call this term. I want to make clear this is a term 2, right? So you can't do like the product of positives and negatives because this is not a product. Just be aware of that. And then term 1, I'm going to actually kind of subdivide this just to really be clear about this. Term 1 has two factors, 4x squared and f double prime of x squared. That's the part we're going to have to talk about. Okay, but 4x squared, hey, that's also positive for any value of x except 0, right? At 0, this is 0. So 0 is still like a subdivider there. But that means anything left of 0, this factor is positive, and anything right of 0, that factor is positive. So that's good. So we really just need to know what f prime of x is doing, specifically f double prime of x squared. And so if we go back up, they told us some stuff. They told us that f is concave downward on negative infinity to 0 and concave upward on 0 to infinity. So it's very tempting now to go in here and do like a negative and a positive, right? Negative infinity to 0, concave down, f is, so f double prime would be negative, and then positive here, concave up. However, keep in mind what it said. It said f is concave down for these x values, right? Negative infinity to 0 and concave up 0 to infinity. But keep in mind, this is not f double prime of x. This is f double prime of x squared. And so what that means is that over here, when x is negative, x squared is still positive. So here, let me just kind of write that out. X is negative, but x squared, whoops, I was going to write squared, let me write it this way, is positive for those negative values of x. And so that actually puts us here. So f is concave up on this interval well, f of x squared, right? Like, well, f double prime of x squared has to be positive there because for these x values, x squared is positive, which means f double prime of x squared is positive. That's what that means. I don't know if that totally makes sense. Think it through again. Just again, work from the inside out. Negative values of x squared makes positive. F double prime of a positive number there has to be positive because that's what this says. F is concave up for positive inputs. So that's going to be positive. And then same thing over here, right? That's also going to be positive. The point being that both factors of this second or first term are positive on both intervals. And the second term is also positive on both intervals. And so certainly everywhere but at 0, G double prime is going to be greater than 0. We can say that. That's kind of our conclusion here. So G double prime of x is greater than 0 for all x not equal to 0. And we also know G double prime exists everywhere. From up above, we said that. Because all these things are positive for all x values not equal to 0. So you could list that. Because this, and this all must be greater than 0 for all x not equal to 0. I would write those out. And then if I was being very thorough, right? But I got a class coming in, so I'm going to wrap this. Therefore, G is everywhere concave up is my conclusion to this. All right, so it's a little tricky, a little bit going on in that one to think about. Anytime they define a function in terms of another function like that and don't give you much to go off of, you just got to take what you get and work with it and think, what can I prove here generally and kind of abstractly. All right.